Right, today we're going to go through our momentum equation again. So this is the momentum equation that when it comes to problem analysis, um, when we consider momentum equation, we will consider what happened in the control volume and what happened in the control surface. So again, the basic fundamental equation for momentum is you take the mass times the velocity mv. So if you take the rho times the volume, you get mass. Mass times the volume, you get momentum. Same with this over here. All right. So you take rho times the velocity times the area, you get volume flow rate. Volume flow rate times the velocity, you get mass flow rate. Yeah? So last time we already covered a few examples. Today we're going to look at 2 examples. Then we go for NC simulation. So let's say you're having a scenario. So your boss give you a statement saying that if you put a tank on a scale, so you want to weight this water tank. So there's a weight there. There's a scale there to weight this water tank. So the water come in from the top and then go up to the side. So what your boss saying that is that the scale will read the weight of the volume of the water plus the tank weight. So that we can treat this as simple static problem. However, we disagree, claiming that the flow analysis is required in this case because the flow is flowing into the control surface and something happened to the control volume also. So you need to prove to the examiner or to your boss that you cannot treat this as a simple static problem because there's a dynamic problem happening here. Okay, so you are given a few parameters. So you are having a metal container which is 0.6 meter high here, and you have a inside cross-section area of 0.9 meter square. So the area of this cylinder is 0.9 meter square. The weight is 2.2 Newton when empty. So when you do not have water inside the tank, the reading on the scale is 22.2 Newton. The container is placed on the scale and water flow into the opening on the top and then went through the 2 opening at the bottom here. So under steady flow condition, the height of the water in tank is 0.8 meter. So the H is 0.8, the total height is 0.61 height. So we need to use the momentum equation to solve this question. So the area for section 1, 2, and 3 is the same, is 0.009 meter square. The velocity is in the y direction. We are given the axis at the bottom here. So we have x direction and y direction. So in this case, our velocity that enter into point 1 here will be negative 3 j unit vector here is going down. So you have negative j meter per second. All right, we need to prove that the weight on the scale is not equal to the static problems. So how do we solve this one? So the first one, we need to, since we are using the momentum equation, we have two equations, 2 terms. One is on the control volume, one is on the control surface. So we need to contain your calculation with the control volume. Or in ANSYS, you contain it with your calculation domain, right? So this is the thing. So when you present your projects or anything, you need to show your domain. Make sure that you are simulating the correct object. So the volume is coming in and then coming out on both sides. You have W of the water tank and W weight of the, you have a weight of the water tank and also the weight of the water that going down. This is including the free body diagram already. And there's a reaction force from bottom that balance the whole system. Okay, so we are focused on this control volume and what goes in will go up. So we will calculate what is Rx in this case. All right. So we will have two governing equation. On the top is again is a momentum equation, m times v, and the bottom one is the conservation of mass equation, which is the mass. Rho times volume, you get mass. All right. So it's important that you can identify these two. Yeah. We have a few assumptions. The first, we will assume that the flow coming in and going out is a steady flow, so that we can maintain these two equations. Momentum will be constant. The mass will be conserved. Will be constant. We are having incompressible flow throughout the control volume and control surface, and we have uniform flow going out and coming in to all the section here. So based on your assumption, when you have a steady flow, you can cancel the first term of your mass conservation equation, where this one, because steady, so when you have a steady flow, the mass over time will be 0. So this one equal to 0. Same with the control volume for the momentum equation. So anything that deal with the steady flow, the first term will through the control volume will be 0. So the next is just the simplification of our equation. So for our total force, the first equation for the momentum is our force will be equal to body force plus the surface force, equal to integration of our simplified equation, with the integration of your momentum through the control surface. And the second one is the conservation of mass equation. All right. Now again, body force is deal with gravity, which is your mg or your weight. Surface force is what happened to the surface. So we are looking at a y component in this case, because the weight is weighting on all the y component. So we are writing focus these two equations in a y direction. So your force will be body force in y direction plus your surface force in y direction, equal to the integration of what happened in the y direction. So later on, the velocity, you will change to small v, right? So if it's in the x direction, then you change to u. In the z, you change to w. Yeah? So in this case, we focus on y. So later on, you'll see the velocity term will change to small v. All right. So your surface y will be equal to your ry. Right. Your surface force at y direction will equal to your ry component. So how to calculate your by? Your body force due to gravity will consist of these two. So by equal to negative of your, because if you write, before you arrive at this one, you write body force in y direction plus W of the tank, weight of the tank plus weight of the water, H2O equals 0. So this is the body force direction. So when you reapply or when you rearrange, you get the equation on the screen here. Then to calculate the weight of the water, you use the rho g times the volume. Rho g times the volume, you get the weight of the water. So to use the parameter given, how you calculate the volume, you take the cross-section area times the h of the water. You will get the volume of the water. So rho g, these two combination is a specific weight of the water. Rho g equal to specific weight. So you can simplify rho g equal to rho gv equal to specific weight times the A times the H. All right. Then after that, you put in all the terms together. So you know that your force surface in y equal to Ry, your By body force in y direction equal to the tank and water. Direction is negative, negative. And the weight of the water is rho is specific weight times the AH. You put everything in one equation. So these three will go in here, and then your momentum equation, you replace this term with V, and then the focus area is section 1 here. Yeah. So you will have again, how you know that you get a negative sign here. You need to know how to draw the surface area, so the surface momentum, surface the momentum, yeah, so the free body diagram for your control volume. So let's say this is your section 1. So you have two terms here. One is your area, one is your velocity vector. So area vector will always pointing out to the opening. Okay, opening always pointing out. Then you look at the velocity given. Velocity is going in. V1 is going in. So if you have a opposite vector like this, the product, the dot products V1 dot area opening going this way, you'll get a negative sign for rho V1 dA1. Any question for the vector direction of this one? Ask me, because later I will ask you for section 2 and 3.
No, sir.
Okay, why you get a negatives here? Why you get a negative sign here?
Because the velocity is going downwards, sir.
What is the dot products of this term? What is V vector dot dA?
Yes. It's then
Okay, I explain one more time. We look at opening number 1. You have area opening here. Area always pointing out. Your A opening pointing out. Look at the velocity at section 1, velocity going in. V1 vector. The products of these two arrows, you take vector velocity dot A vector, you will get a negative products of V1 dA or negative V1 A1. You get a negative, again I repeat, you get a negative, it is because you have an opposite vector direction. The dot product will give you negative. I repeat one more time. Why you get a negative? Because the vector direction of these two products, if you take vector V1 going down, dot area vector products of going up, this opposite direction give you negative products. Are you clear, Pitiba?
Yes, sir.
Okay. I will ask you on section 2 and 3. Okay. So the velocity at y direction, we look at section 2 and 3 here. There is no velocity in y direction. There is no direction in y direction. So for 2 and 3, there is no v term in the equation. Okay. So this is for your moment equation that you arrive at v1 times negative rho v1 a1. Okay. So you have one term and then the three terms over here. You put into the equation, put in here, and then you replace this one, you'll get this equation. Okay. Next, you continue to solve. So once we get this one, you substitute all the value inside there. All right. So we need to take note of your V1. Your V1 is a y component velocity. So you can write your this one, your V1 will be equal to negative capital V1 is a big velocity here. So at the end, you will get V1 squared in the equation. And you calculate, you're substituting all the value inside there with all the parameter that is given. Your Ri will be 614.8 Newton. So that's why your resultant force or your reaction force at y direction, at the scale, at the weight there, you will get 614.8 Newton. Okay, so if you use the static problems, you won't get 614.8. You will get more than here, more than 614. Okay. If you take weight of the water times the weight of the tank, you will get more than 614.8. Okay, meaning you only focus on static problem, you only focus on these two. Okay, this is a static problems. So if your customer say that this one can treat as a static problem, the argument is wrong. You need to use momentum equation and conservation of mass equation because there's a dynamic problems that the water come in section 1, going out in section 2 and 3. Okay, we're done for the first tutorial question. The second one, we will apply the same equation to this scenario also. So let's say we have a water that go steadily at a 90-degree bend here. However, there's a change of cross-section area from section 1 to section 2. So the absolute pressure is 220 kilopascal, and the cross-section area is 0.1 at section 1 here. So at outlet, the cross-section area over here is 0.0025 meters square. Velocity is 16 meters per second. So the elbow discharge to the atmospheric here. Determine the force required to hold the elbow at place. So we need to determine what is the force that keep this elbow from dropping or from flying away. So we need to find the force so that we can choose the correct material for this element. So again, we have all these parameter. The absolute pressure is 220 kilopascal. A1 area is 0.1 meter square. A2 is 0.0025 meters square. Velocity at section 2 is going down because you are giving the axis x to the right, y going up. So our velocity is negative 16 j vector because it's going down in y direction, meter per second. So we need to find the force at this section. The next things, every time we consider a control volume or control surface or a domain, then we need to simulate or model the domain. So we will choose from the diagram on the top here into a diagram that you see on the bottom of the screen here, which is given by the square. So you have section 1 and section 2 given by your velocity going in and velocity going out. Now, by having said here, before we go for the equation, I want to find, let's say this is your area vector. This is your area vector also. Area vector section 1, area vector section 2. What is the products? What is the products of V1 times A1 products? Is it positive or negative? What is the vector products of V2 dot A2 product? What is it positive or negative? Okay, Pratibha, explain what is the products of vector V1 dot A1. Is it positive or negative, and explain why?
Wait, sir. So V1 times A1 should be negative, sir.
Why? Why
Okay,
you claim it's negative?
V1, okay, the V1 is in X direction,
Mm-hmm.
so it's positive.
Mm-hmm.
While since the position of vector should be opposite, so the A1
How you know it's positive? How you know that how you know is opposite?
because okay, wait,
V1 you
sir,
already
wait.
explained. What happened to the area vector?
Oh, sorry, sir. The A1 also is positive, sir.
Means A1 also go to X direction.
Okay, because it said inlet cross sectional area A1 is 0.01 meter square. So the A1 should be positive.
I'm asking
Yeah.
you about the vector of A, of area.
Okay.
So
Okay.
positive means your area is going X direction, correct?
Yes, correct.
And then your velocity also going in like that.
Yes,
Fine.
yes.
Okay,
It's going X direction, so it should be positive, sir.
positive.
They are not opposite.
Okay. I repeat one more time. If you have an opening and you have a section 1, for area vector is always pointing out. This is your section 1. Your section 1 area is pointing out like that. So your vector A is in this direction. Opening, all the opening always going out, whether is doesn't matter what is the orientation. When you have an opening, you're always pointing out for area. Okay. So by having this explanation, the velocity will be going in, V1. So the products of V1 dot A, you'll get negative sign. Yeah? Do you understand?
I understand, sir.
So why the products of V1 dot A1 you can get negative?
It's because different position of vectors, sir.
Okay, so what mistake you did just now?
I assume the area is positive side, sir.
Okay, so again, this is the last time I explained about the area vector. The area vector is always following the opening. It's always pointing out. Okay. All right. So the next one is you draw the free body diagram on the control volume or control surface that you draw just now. So if you draw the control volume, all the atmospheric pressure will acting on all the area. Plus, there's a pressure that coming in from the left inside the pump, inside the pipe here, and then you have a body force. All the mass, all the body on the Earth, on this Earth will have a mass. So when you have a mass, you always have a gravitational force effect, where the products of mass times g mg, you get weight that is going down in y direction. So in here, you have two components here. You have two reaction force. One is to the x direction, one is to the y direction. When in this case, you can minus all the effect of atmospheric pressure and straight away use gas pressure in the calculation. So the products of the actual free body diagram minus the atmospheric pressure, you get a clean net pressure, or you get a clean, more simpler control volume with the pressure force. Here you see a small g here. It means that you are reading from sensor, pressure sensor, or gauge pressure. Okay, so and then we will use this diagram for calculation. Governing equation, again, pull out the two. One is momentum equation. Again, how you identify that the first one is momentum. Equation for momentum, m equal to mass times velocity. Momentum equal to mass times velocity. Rho times volume, you get mass. Mass times volume, you get mass times velocity, you get momentum. The second one is conservation of mass. How you know is mass. Rho times volume, you get mass. So this is how you identify these two equations. We have a few assumptions here. We have a uniform flow. We have an atmospheric pressure at 101 kilopascal absolute. If we measure from absolute, we have a compressible flow. We have a steady flow, and we will ignore the weight of the elbow and water in the elbow. So with this assumption, we can cancel out the first term for our momentum equation because we have a steady flow. Same with our conservation of mass equation. We can cancel the first term. Then these are the two equations after we simplify the equation with the assumption. And in this case, we focus on x component of the momentum equation. So we modify these two equations in x direction. So again, the velocity term in the momentum equation here, in x direction, it will be u if it's in x direction. If it's in y direction, it will become v if it's in y direction. So the first equation, we focus on x direction. So Fx equal to F body force in x direction, surface force in x direction, equal to integration of area u rho v dot dA. So again, we are focusing on the products of velocity and area. So expect you'll get negative sign at section 1 as what we discussed just now. So for section 1, we don't have vertical force. We don't have body force at section 1. So we also don't have U at section 2. At section 2, the velocity is going down. There's no velocity in x direction at section 2. There's no velocity at this direction. So you cancel the first body force, and you replace your surface force with catch pressure plus the resultant force in x direction, like what you see on the top of the diagram. You have pressure gauge, uh, uh, value, pressure at gauge, right, plus Rx. You get the term on the right hand side. Then you copy the momentum term at the right hand side. Then you do the dot products like what we discussed just now. You take the v vector times the area vector. Okay, we are interested to find the resultant force in x direction. So we rearrange the equation. You get negative p gauge times area 1 plus the integration of your momentum equation for section 1. Again, you should be able to explain why there's a negative sign there. All right. So you rearrange the equation, and your V1, your U1 will be equal to V1. So you times inside there, you get V square 1 square there. Okay. The rest is just substitution of value. So in this equation, there is no V1 value given here. So you need to find. So to find V1, you need to use the conservation equation. This one, this is a conservation of mass equation. So you find what happened in the control surface will equal to what coming in section 1. Your mass dimension, yeah, we're looking at mass dimension, the mass flow dimension. What come in will go up, will be the same. So if you can see here, we have two integration for surface 1 and surface 2. The rest is still the same. You get mass flow rate at section 1 plus the section 2, this one. And you're still seeing the dot product here, a vector dot products. So again, you should know that if I mention section 1, you should see from here you get a negative sign after you convert the vector sign into a scalar form. Area always pointing to this way. For section 1, opposite direction, you'll get negative for the first term. Area always pointing out, you'll get A2. Same direction with V2, you get positive value for the second one. Okay, you'll get this term. So After you substitute all the value, you will get V1 equal to 4 meter per second. You substitute back into the equation just now, you'll get your Rx. Right? Your Rx will be negative. It means that what you assume is wrong. The actual one is your Rx is going this way. Okay. Next, you find your Ry, y component. You repeat the same. You calculate for forces in y direction. You take By plus Fxy equal to integration of your momentum equation. Again, this time the velocity you change to V because it's in y direction. And you repeat the same for Ry. So here you should know why there's a negative sign there. Right? So continue with the calculation. You get Ry equal to negative 600 something Newton. So again, your Ry is going down like that. So from here, you find your Rx is negative something. Okay, negative something. Negative something. Ry equal to negative something. So you can find the resultant force or the total force of your Rx and Ry. R total equal to square root of Rx square plus Ry square. You get the value. And how you find the angle, you need to plot the graph. So your Rx is going this direction. Ry is going this direction. So you can plot the angle. Okay, the angle is going this. These two will give you. Okay, your Rx is like that. Your Ry is like that. Rx, Ry. From the start point to end point, you get your resultant vector. Theta here, you use the tangent to find the angle. You have Rx and Ry already. You use tangent to find angle. So you get your R total at a certain angle. Okay. So in this tutorial, we do not go through the total, but we need to find the Rx and Ry because as long as our structure is strong enough to hold in X and Y direction, then we are fine. Okay. Okay, I think we stop at these two examples. Let me stop the recording.